So today in this video, we're going to discuss the Carnot engine. And in particular, we're going to see why the Carnot engine is the maximal efficiency engine. That is to say, you could never have a heat engine operating with heat reservoirs, TC and TH, with a hot and a cold reservoir at those same temperatures, and have it be more efficient than a Carnot engine operating with reservoirs at the same temperature. So, as I said, we're going to see how if there was an engine that was more efficient than a Carnot engine, then it would violate the second law of thermodynamics. So there are many ways to state the second law. So let's think about one of them. So one of the ways of stating the second law of thermodynamics is in terms of entropy. So the total entropy, or the total change in entropy of the universe for all processes is always greater than or equal to 0. And this is one way, this is equivalent to all of the other ways of stating the second law of thermodynamics. This is just one particular way of stating it, is that if you consider some process and you really consider everything involved in the process, you know, if it's an experimenter in the lab, you also have to consider the experimenter. If you consider everything involved, the change in entropy of the universe, of everything, is always greater than or equal to 0. And so it turns out that this is going to be equivalent to the statement that no engine can be more efficient than a Carnot engine. And how we're going to see that is by the fact that if an engine, we're going to hypothesize that perhaps we did have some engine that was more efficient than a Carnot engine, we'll see that if that were the case, then we would be able to write down a process such that the change in entropy of the universe was less than 0, that the change in entropy was decreasing. So just quickly, let's remember what a Carnot cycle is. So if we draw our very familiar PV diagrams, then a Carnot engine starts at some particular temperature, it moves down an isotherm, and then adiabatically decreases in temperature, then moves back up an isotherm, and then adiabatically increases in temperature. So what we have here, right, so this is an isotherm. Likewise, this sort of lower leg. And then these other two are adiabats. So that is to say, again, of course, isotherms are constant temperature processes. So along each of these two legs, we know that it has some constant temperature, whereas these other two, where it's changing in temperature, these are adiabatic processes, and so therefore we know that there's no heat exchange. So what's really happening is that so here, well, I guess depending on which direction you're going, along one of the isotherms you're inputting heat to the system, and then along the other isotherm you're dumping heat back out into the world, depending on which direction you want to move around this. So in order to show that this is the maximally efficient engine, what we want to do is we want to consider putting two engines together. So now I should say actually one really important point about Carnot engines is that they're completely reversible. So again, this is very idealized. We know if we were really building something completely having no losses to friction or things like that is not going to happen. But theoretically, a Carnot engine is completely reversible, which is to say you could go around in one direction, which is really a Carnot engine, or you can move in the opposite direction, which is actually a Carnot refrigerator. So these are completely reversible. So what we want to do is we want to consider a scenario where we have some hot reservoir up here at some temperature TH, and then we have some cold reservoir down here at some temperature T cold. And then what we want to do is we want to say, let's say we have some super engine, and let's pretend momentarily that it's more efficient than a Carnot engine. And then over here on the right, what we're going to have is actually a Carnot refrigerator. So it's going to be working in reverse. And so what we're going to do is, so what the super engine is doing, it's taking some heat energy from the hot reservoir, and then it's going to dump its waste out as some more heat into the cold reservoir. And then in between, so it's going to output some work. You know, it's an engine, it's doing something useful. So it's going to output some work, and then that work is going to be what we're going to do to power our Carnot refrigerator. So now it's a refrigerator, so the Carnot engine, or the Carnot refrigerator, is going in the opposite direction. It's dumping some heat into the hot reservoir. And so it's taking heat from the cold reservoir and dumping it to the hot one. So that's what a refrigerator does, right? Its heat is moving in the opposite direction than an engine. And so again, so we have this super engine, which is, we're going to suppose, is more efficient than the Carnot engine. It's doing some work. We're going to use that work to power our Carnot refrigerator, which is going to then take heat from the cold reservoir and put it in the hot reservoir. So let's assume that such a thing could occur. Well, we can do such a thing. Let's assume that this super engine is going to be more efficient than our Carnot engine. So again, what I started by saying is that the fact that no engine can be more efficient than a Carnot engine is related to the fact that the entropy of the universe is always increasing. So what we want to do is think about the entropy in this process here. Let's think about the change in entropy of all of the systems. So it turns out that for reversible processes, so for all of the processes in this cycle, the change in entropy is actually going to be 0. So I guess actually maybe a better way of saying this is, so for both the super engine, so the entropy of the super engine and the Carnot engine, we know these are cyclic cycles in either case. And so they're starting in some state, and after a complete cycle have ended in the same state. So because the entropy is a well-defined property of a state, we know that the initial entropy of the super engine must be equal to the final entropy, because it ends after one complete cycle. It ends in the same state as it started. So the change in entropy of the super engine is equal to the change in entropy of the Carnot refrigerator is equal to 0. And again, that's just because you can think of this as just because these are cyclic processes. They're ending in the same state that they began, so they must end with the same entropy that they started with. Their change in entropy is 0. So what we'll consider instead, so we're talking about the entropy of the universe again. We have to think about the entropy of everything. So what we can think about is the change in entropy of our reservoirs, right? So we know we're dumping some heat or taking some heat out of these reservoirs. So they're also going to, well, they potentially could experience some change in entropy. So what we really want to compute is that change in entropy, because these are just going to contribute 0. So because the reservoirs are just at some fixed constant temperature and you're adding heat and they're staying at that temperature, then that's an isothermal process. And we know for an isotherm, the change in entropy is given by the heat divided by the temperature of the thing that you're considering, so the temperature at which you're at. So we could think about the total change in entropy of the reservoirs, so both of them, is equal to being careful about the signs. So we could just write the total change of entropy of the reservoirs, or, equivalently, this is the change in entropy of the universe. Because these other guys contribute nothing, we can just write it in terms of these heat exchange processes and the temperature. Now we want to relate this to the efficiency of our engines. So let's remember the efficiency. So the efficiency of our super engine is the work that it does divided by the heat that it brought in. And the efficiency of the Carnot engine is equal to the work that it would bring in if we were working in that direction, divided by the heat that it would be using. And so let's see, so we need these, and then the final piece, so we can relate these to each other, I guess, if we want. So these two combined can give that. So we know this work is the same, right? This is the work that the super engine is putting out is exactly what the Carnot refrigerator is using. So we can cancel out this, set these two equal to each other, cancel out the work, and get that this is a ratio of the efficiencies. Right, so it's just a little bit of algebra. And then finally, what we'll use is the first law of thermodynamics, which again is the law that really just tells us about conservation of energy. And with this, we could find that QC is equal to minus W plus EC over ES QH prime, where I've used sort of this above result here, and we'll run a little on space. But QC prime, again using the first law, is equal to minus W plus QH prime. So again, this is just energy conservation. So now if we use all of these things and plug them back into our change in entropy of the reservoir, so the change in entropy is equal to, with a little bit of simplification, but hopefully you can do the algebra at home. So this is sort of our final expression right here for the change in entropy of the reservoir, or equivalently, the change in entropy of the universe. Right, so what we want to use is we want to use the second law of thermodynamics that tells us that for any process, the change of entropy of the universe, the total change in entropy, has to be greater than or equal to 0. So let's analyze each piece of this and see whether it's positive or negative. So of course, we always define the hot reservoir to be at a higher temperature than the cold reservoir. So if we look at this final term right here, so this is always positive. Let's see, can you see that? Always positive. And then QH, similarly, we defined this is positive, we just defined our variables such that QH prime is a positive number. And so what that tells us is that if we want this whole expression to be positive, then this, so that all implies, must be positive. If you can read that, sorry, that's a little sloppy and small. But this middle term must be positive for the total change in entropy to be 0. So this implies our real result, which is that EC over ES must be greater than or equal to 1, or equivalently, I guess this also implies that EC must be greater than or equal to ES. So this is sort of, maybe I'll, use like 6 different colors to box this one, because this is really the big result that we are after, which is that we were able to show that in order for the change in entropy of the universe to be greater than or equal to 0, which the second law of thermodynamics tells us must be the case, then we found that the entropy of the Carnot engine, or the efficiency of the Carnot engine must be greater than or equal to the efficiency of our super engine. So it turns out that we wanted to build the super engine and have it be more efficient than the Carnot engine, but we failed. Maximally, it could only be as efficient as the Carnot engine. So this is one way of proving the fact that no engine can be more efficient than a Carnot engine, and the fact that this is really just an equivalent statement to the fact that the entropy of the universe must always increase. So I think that's mostly what I wanted to say. The last thing I guess I wanted to note is that really the reason the Carnot engine is the most efficient engine is really because it only contains reversible processes. So really the true statement is that reversible engines, so engines with only reversible processes, are the most efficient engines. And the Carnot engine is just one particular example of a completely reversible engine. You can imagine writing other engines down that were also completely reversible, and then you would find that that would be the case where you have this equivalence, where you have that their efficiency is exactly equal to the efficiency of a Carnot engine. So hopefully that cleared some things up, proving to you why the Carnot engine is the most efficient of the engines. Thanks.